Hello everyone, welcome to my channel. In this video, I'll discuss the topic superacids and Hammett acidity function. But before going into the topic superacids, first let us know what are acids. An acid is a substance which gives proton in aqueous medium. This is a very simple definition of acid and was given by Arrhenius, and we know this definition from our school level. There are some other definitions of acids and bases are available now, but we don't need to know those definitions for today's topic. Anyway, acids can be divided into two types, strong acids and weak acids. HCl, HNO3, H2SO4 are considered as strong acids as they are 100% dissociated in the aqueous medium, whereas CH3COOH, that is acetic acid, benzoic acid, are considered as weak acids as they are not fully dissociated in aqueous medium. In aqueous medium, we generally use the term pH to quantify the acid strength of the acid solution, and pH is expressed as minus log of concentration of H+, and pH ranges from 0 to 14, means if the H+ concentration is 1 normal, then pH will be 0, and if it is 10 to the power minus 14 normal, then pH will be 14. So, we can use the concept pH for 1 normal to 10 to the power minus 14 normal H+ concentration. Beyond that, means if the acid concentration is 2 normal or 4 normal or 5 normal, etc., then we cannot use the concept pH. Okay, what does it mean? It means that pH concept is actually applicable in dilute acid solution, not in the concentrated acid solution. Okay, this is very important to understand the concept of superacids. Now let us know what are superacids. Superacids are some liquids which are many times more acidic than the so-called strong acids like 100% pure H2SO4 or HNO3. As I said here that H2SO4, HNO3 are strong acids, but 100% pure H2SO4 or HNO3 is weaker acids in compared to the superacids. For example, HFSBF5 or HSBF6, which is known as fluoroantimonic acid, HSO3F-SBF5, which is known as magic acid, and triplic acid, that is CF3SO3H. These are some common examples of superacids. As I said earlier, that the concept of pH cannot be applied for concentrated acid solution, as these superacids are much more acidic than the 100% pure H2SO4 or HNO3. We cannot apply the concept of pH for these superacids. So, here another term known as Hammett acidity function is used. Hammett acidity function is defined as the protonation equilibrium of a very weak uncharged base, typically an organic indicator base like nitroanilines, and its conjugate acid. Consider this equilibrium BH plus to B plus H plus, where B is the base like nitroanilines. This H plus is supplied by the strong acid like superacid in this case. Okay, now for this equilibrium, if we define the H0, that will be pKBH plus log concentration of B divided by concentration of BH plus. We can derive this expression. For the equilibrium, if we write the KBH plus, then it will be activity of B into activity of H plus divided by activity of BH plus. Now, if we write this expression in terms of the concentration, then we have to include the fugacity term, and it will be like this. Okay, the latter term, that is FB into FH plus divided by FBH plus into concentration of H plus, is abbreviated with the small h0. Okay, now from this equation, if we derive the h0, then it will be KBH plus into concentration of BH plus divided by concentration of B. Now let's take logarithm, negative logarithm in the both side. Then what will be the equation like this: minus log H0 equal to minus log KBH plus minus log concentration of BH plus divided by concentration of B. This term in the left hand side is actually H0, and it is the minus log of KBH plus will be the pKBH plus, and if we take the reciprocal of this, then we will get the plus term here, and it will be plus log of concentration of B by concentration of BH plus. This expression I have already showed in my earlier slide. So this H0 is called the Hammett acidity function. As I replaced minus log H0 as the capital H0, so we can write H0 equal to minus log of H0. Now what is the H0? H0 is FB into FH plus divided by FBH plus into concentration of H plus. Now if we ignore these F terms, then only concentration of H plus will be left. Okay, where we can ignore this? In the dilute acid solution or dilute solution, we can ignore this term. Okay, so how it will look like? It will be H0 equal to minus log of concentration of H plus. And I showed earlier that minus log of concentration of H plus is actually the pH. So H0 becomes pH in dilute solution. This is a very common question in the undergraduate level, and it is asked to show that Hammett acidity function becomes synonymous to pH in the dilute solution, and I showed this. So in dilute solution or in aqueous medium, the H0 becomes synonymous with the pH of the medium. Okay, anyway, now this H0 or the Hammett acidity function is used to quantify the acid strength of the concentrated acid solution or superacid. Okay, so more negative is the value of H0, more is the acidity. Like pH, less pH means more acidic, higher pH means less acidic. Here also like that. Now let's compare the H0 value of some acids. This is pure H2SO4, which has the H0 value of minus 11.93 or around minus 12, whereas fluoroantimonic acid has the minus 28, magic acid has minus 23, triplylic acid has minus 14.9. So you can easily understand from these values that all are more acidic than concentrated or the pure 100% pure H2SO4 solution. Okay, so what is the use of superacids? Superacids are highly valuable tools in chemistry, primarily used in catalysis. They are used as catalyst in industrial processes like petroleum refining for hydrocarbon isomerization and alkylation to produce high octane gasoline. And another important use in the organic chemistry, by using the superacid medium, we can easily stabilize the carbocations or other highly reactive intermediates. For example, tertiary butyl carbocation can be easily generated in superacid medium from tertiary butyl alcohol. Okay, that's all for this video. Thank you all for watching my videos.